Okay folks, this week we're going to stop looking at probability and start looking at some good old-fashioned number work, estimation, rounding and bounds. So I will give a little reminder of rounding before we go any further. This is something that I think was back in chapter 1, but just to point out that all methods of rounding are essentially the same, it's just where you decide to round it. 5 or more round up, 4 or less round down. You can read that definition yourself. Do remember that everything after the point you've rounded to goes to 0. You might want to have a go at these 6 as just a quick example, and let's just check what you've got. So 2 decimal places, we want to go to the second decimal place, which is a 9. There's a 2 after it, so we are essentially rounding down. So it's going to stay 1.29, then everything else goes to 0. And you probably just write that as 1.29. Here we're rounding to the nearest 10. The 10s are here. There's a 5 after it, so we're going to round up. So that's going to go up to 16, and everything after it goes to 0, so 160. 1 decimal place is a 9. There's a 9 after it, so it rounds up. 9 kind of rounds up to 10, so you need to carry 1 over. Everything else goes to 0, so just 6.0, or you could just have 6. The tenths are this column. There's a 5 after it, so we'll round up. That means we'll go up to 40.10, which is just 40.1. 1 decimal place here. Well, the first decimal place is here. Sometimes you have to add in bits if they're not there. There's nothing after it, so it's going to stay 85.0, and you might want to say that as 85. Lastly, unit means to the nearest 1, or nearest whole number, or nearest integer, they could say. Our integers are here. There's a 0 after it, so it's going to round down, and everything else goes to 0, so it's just 0. Another thing that we looked at in chapter 1 was the idea of significant figures. Again, just want to give you a little bit of a reminder here. The first significant figure is the first non-zero digit, so you don't start counting until you get to something that isn't a 0. The second and third can be zeros, and you just count from that point. So if we were looking at 1.2928 here, the first significant figure would be the 1, because it's the first number that isn't a 0. The second significant figure would be the 2, the third significant figure would be the 9, and so on and so on. So if we're rounding to 2 significant figures, we find the second significant figure, which is a 2. There's a 9 after it, so that rounds up. Everything else goes to 0, and so it's just 1.3. For the second one, the first significant figure is the 1. There's a 5 after it, so it's going to round up. So it's going to go up to 2. Everything else goes to 0, and that's just 200. A mistake that people make there is just write down 2, but your number has to look like what you started with. If this was 150, our answer has to still be in the hundreds. Third one, first, second, third significant figure is this 9. There's an 8 after it, so it's going to round up to 0, which means we're going to carry 1 onto the 9, which means we're going to carry 1 onto the 9, so we're going to end up with 6.00. You could just write that as 6, but it's useful to show the 3 significant figures that you've got, so I am going to leave it as 6.00. Next one, 4 is our second significant figure. There's a 9 after it, so it rounds up, so we go up to 55. Everything else goes to 0, and nothing needs doing with that. Okay, second row. You start counting at the first thing that isn't a 0, so our first significant figure would be the 5. Our second significant figure would be the 0. You can count zeros after you've started. There's got a 7 after it, so we're going to round it up. So everything else goes to 0. We're going to have 0.051 there. Have a go at these next 3, and let's see what you got. So our third significant figure here is the 9. There's a 0 after it, so it stays the same, and everything else goes to 0, so 1090. Our first is the 4, 8, so our third significant figure is the 9. There's a 9 after it, so it rounds up, so we should end up with 0.0490. And for our last one, the first significant figure is the 9. There's a 9 after it, so it's going to round up. Everything else goes to 0, so we'll end up with 10,000. Hopefully you got them right. If not, it's probably worth having a quick check on rounding to significant figures on Hegarty first. One last reminder, again, this is something that was touched on in chapter 1. is estimation, which is just the idea of rounding first and then finding out a much easier version of the answer. So let's look at a few little examples here. If I had 4.89 times 3.12, I would change that to 5 times 3. Now we tend to use this little squiggle equals sign to show that we've done an estimation because those are not equal to each other, and then we can say that our estimation is 15. This one here I would probably change to 54 divided by 9 because I know that goes quite easily. I'm always trying to come up with a sum where it divides nicely. Essentially, you want this to be something you can do in your head. For the next one, you want to show all of the rounding that you've done, so we should do that first. Feels like 29.9 is going to go up to 30. Might change that to 40. Might change that to 3. Might change that to 4. It's not set in stone, you know, you could change them to other things if you want, but again, there's no point in giving yourself a difficult sum just because you feel like one. An estimation should just be rounded. That will give us 1200 on the top, 12 on the bottom, and so our estimate for that answer is 100. And the last one, we've got a square root. How am I probably going to round this? Well, I could say that this 27.6, could maybe say that's 30. This 0.48, I could maybe say that's a half. Something I would never do, by the way, is round this up to 1 or down to 0. You do have to think about at least the first figure. And then what would that give me? 30 divided by a half is 60. And the square root of 60, well, we know 8 squared is 64. We know 7 squared is 49. So this is somewhere in the middle. So I would estimate this as being something like, I don't know, 7.6. It's closer to 8 squared than it is to 7 squared. Quite often in GCSE, however, they tell you what to round to because they want to limit the amount of different questions that they might have to mark. So here's a standard sort of gambit for an estimation question. Estimate by first rounding to one significant figure. So first thing you should do with these questions is round your numbers. Let's go through the first one. Those are our first significant figures. We're going to round them both down because they've got a 1 after them. So this would just be 5 times 3. And so our estimate for this answer would be 15. For the second one, we're going to round this up to 20 divided by 4. And so our answer would just be 5. For the next one, 3 numbers to round here, and just be careful. This one I think is a little counterintuitive if you just round it as you would. We've got a 10 here as our first significant figure. There's a 3 after it, so it's rounding down. So this is going to become 10. There's a 6 here, there's a 1 after it, so that rounds down, so that becomes plus 6. And then the first significant figure on the bottom here, don't round this to 1. Our first significant figure is the 5, so we're going to need to round it down to 0.5. So we'd get there, once we've tidied it up, square root of 16 divided by 0.5, which will give us 4 over a half, which is 8. A lot of people are going to get the answer 4 there because they'll change that bottom number to 1. Now, you can be asked to say if your estimates are bigger or smaller than the real answer that you should get. So we have to think about whether we round it up or down. Just want to use that first one as an example here. This one here. We rounded down both of our numbers. So this 15 is going to be smaller than the actual answer. So we would call this an underestimate. You might need to explain that, saying it's an underestimate because we rounded everything down. When it's divisions, you have to be a little bit more careful about that sort of idea. So here, we rounded 18 up. So we basically changed it to a bigger number, and then we divided it down. So we divided it by a small number. So if you think about if you took a bigger number and divided it by a smaller number, you'd actually end up with an overestimate. And this last one, you're probably thinking this is going to be, it's kind of a bit of both, isn't it? So the top is definitely smaller than the actual answer needs to be because it's really like root 19. The bottom is smaller as well, however, so you'd have to think about whether they cancel out. So in this case, I think could be either is all you can really say without actually doing calculations. And the whole point of an estimate is that you're not using your calculator. So on the page, you can see 4 GCSE questions. I'd like you to try them out first. I'm going to assume you're pausing now. And let's go through. So again, be careful in terms of what it says. This says approximations. That means you can choose how you round it. I would probably round this to 400 and 2 times 40, which would give me 400 over 80, which is just 5. Obviously there'll be a range of answers you're allowed to get, but that seems to me the one that requires the least work. The next ones tell you what you have to round to, nearest 10. So we know we have to change this to 60 times 50 over 100. That's going to give us 3,000 over 100, which is just 30. The next one significant figure. So that is going to change this to 80 times 10 over 400. So we've got 800 over 400, so that's just 2. And then lastly, one significant figure again. This is going to change to 0.5 times 40 squared. So again, 39.6, there's our first significant figures. And then the square root of 100. So what do we do? Well, BIDMAS wise, we need to do the square first. So that's going to be 40 squared is 1600. Square root of 100 is 10. So we've got 800 divided by 10. Our estimate for that should be 80. So that's kind of things that you've seen before, but we're going to try and introduce a new concept today, which is the idea of bounds and error intervals. And it basically is the opposite of rounding. So here we've got an example of a sort of question we could get asked here. I am 180 centimeters to the nearest 10. What's the tallest and shortest you could actually be? So they have rounded the number. They got to 180. So they might have had, say, 178. Rounded that to the nearest 10 and they got to 180. And what we have to think is, well, what is the smallest this person could have actually been that it rounded? Now, I think the smallest should be okay. We can say 175 centimeters there, can't we? Because 5 or more round up. And you might be tempted for tallest to therefore say 184, because 184, so 4 would round down. If we went up to 5, it would round up. But heights aren't just whole numbers. So what about if we were 184.9 centimeters? That would still round down to 180 to the nearest 10. And so would 184.99, and so on, and so on, and so on. And there isn't really a biggest number here that will round down to 180. We can keep adding on those 9s forever. Now, in terms of actually saying that, well, you could be really smart and use like a little recurring symbol. But we actually just tend to say that the tallest we could be, our upper bound, is anything less than 185. Now, how do we put this all together in terms of the tallest and shortest we could be? So we're going to say the height is in between 175 and 185. We know it's got to be less than 185, because if it was exactly 185, it would round up. But we don't know, it's not 184.9, it's not 184.99, etc. That's as accurate as we can be. And it has to be bigger than 175, but it could be equal to 175. So we use that little inequality sign where it can be equal to. This is called the error interval of the height. This is what the height is inside. It's between 175 and 185. And we call the number that's the smallest, we call that the lower bound. And the number that's the biggest, we call that the upper bound. And the whole thing is called the error interval. So we can try and do the same thing with the next question. 80 kilograms to the nearest 5 kilograms. It's the heaviest and lightest you could actually be. Now a mistake here would be to say something like 75 and 85, because you've got the number 5 in your head. But if you think about what they would round to, 75 to the nearest 5 would go to 75. So we have to be a little bit clever here. So what could we do? Well, 78 would definitely round up to 80 to the nearest 5, because it's closer to 80 than it is to 75. But it actually ends up being 77.5 as the smallest we can go. If we think about, here's 75 and here's 80, the number that's exactly in the middle, which is what we want to find, is 77.5. And Similarly, if we think about between 80 and 85, which is going to be our upper bound, the one that's exactly in the middle is going to be 82.5. So we always want to find that thing that's like halfway between the two things we could round to. So our error interval in this case looks something like that. Our weight is somewhere between 77.5 and 82.5, and we've got a less than or equal to symbol here, and we've got a less than symbol here. So there is our error interval. The heaviest they could be would be 82.5, the lightest they could be would be 77.5. And what we want to try and do on the next page is just sort of summarize this and make it a little bit less guesswork. So in general, if we want to find an error interval, then find what it was rounded to. We're going to halve it, add and subtract. So as a quick example, if I say that I've got something which is 90 centimeters to, say, the nearest 5 centimeters, then let's go through what we've done. Find what it was rounded to. It's rounded to the nearest 5. Halve this. Okay, 5 divided by 2 is 2.5. Add it to the rounded value, so that would give me 92.5. That's my upper bound. Take it away from the rounded value, so 90 minus 2.5 would be 87.5. And then we need to put it in the form that we've got. So less than equal to and less than. Okay. So here are 4 of those sort of questions. I'd like you to write down what you think the error intervals are first, and then unpause the video. Okay, let's see. So rounded to the nearest 10, divided by 2 is 5. So that's going to give us 85 and 95 as our limits. We want to be less than or equal to, greater than or equal to 85 and less than 95. For the next one, nearest 5, so we go 5 divided by 2 is 2.5. Add it to 55 and we'll get 57.5. Take it away, we've got 52.5, and again, make it look like an error interval. Next one says we've rounded to 1 decimal place. Now, if you think about where 1 decimal place is, it's here. That's in the tenths column. So we would interpret this as meaning to the nearest tenth, or even more easily, to the nearest 0.1. So once we've decided that, we can go the same method. We can say, okay, let's do 0.1 divided by 2, which is 0.05. Then add it and take it away from the number. We'll get 92.35 as our lower bound and 92.45 as our higher bound. And then it's the same sort of thing when we say 1 significant figure. Well, the first significant figure here is the 7, which is in the tens column. So this is the same as rounding to the nearest 10. So let's do the same thing now. 10 divided by 2 is 5. Add it, take it away. Our error interval is 65 to 75. So bearing that in mind, I'd like you to try and figure out these 4 multiple choice questions. Okay, let's assume you've unpaused at that point. So we've rounded to the nearest 10 here. 10 divided by 2 was 5. That means our error interval needs to go 35 to 45, and it needs to look like this with the less than or equal to symbol first. For the red question, nearest 100. So 100 divided by 2 is 50. So we want to be going from 750 to 850. We want the less than equal to symbol first, so it is D again. For the blue question, nearest whole number, so that's to the nearest 1, or sometimes they might say the nearest integer, means the same sort of thing. We'll halve that, gives us 0.5, and so we want to be 0.5 either side. We want to be between 19.5 and 20.5. And B is the only option that works there. Lastly, they've recorded it as 90, and they've said the error interval is 89.5 to 90.5. So we actually want to work out what we rounded to. So in this case, think about what they added on to 90. They added on a half, and because we're working backwards, we're going to double that to work out we were rounding to the nearest 1. So the nearest whole number was what they were doing. You could have also had 2 significant figures, but that's not one of our options. Now, there are a couple of situations where you have to tweak the rule, okay? And the first one that we've got to be aware of is if you're rounding things that can't take decimal values. So for example, number of people. So we got here 80 people in a room to the nearest 10. If we go back to our very first thought, 75 people is definitely the smallest amount that would round up to 80. And then if we think about what we were doing before, we were saying, well, it can't be 84 because it could be 84.9 or 84.99 or whatever. That obviously can't be true when we're counting people in a room. The highest number of people that would round to 80 is 84. There's a gap between that and 85, so we can actually definitively say that the number of people is between 75 and 84, including 84. So look how this is different to how it normally is. We could just say the lower bound is 75 and the upper bound is 84 as well. Similarly, a football ground's got 3,400 rounded to two significant figures. So our second significant figure was the 4. So that means to the nearest 100, because that's in the hundreds column. What's the error interval here? Well, half of 100 is 50. And then we've just got to be careful here. So yes, 3,350 is fine, but 3,450 would round up. So we just go up to 3,449. So if it's something that can only be a whole number, watch out. And the other fancy form of rounding that can be used in GCSE is called truncation. And truncation is a word meaning to cut short. And it just means that you're going to chop the number at the point where it says. So we've got one decimal place. Our first decimal place is the 2. And we're just going to chop the number there. So truncated, it's just 49.2. Or another way of thinking about it is you always round down. Third decimal place was the 9. Chop the number there, 2.539. Second sig fig, chop the number there. First sig fig, chop the number there. And then integers are here, so we're going to chop our number there. So yeah, just be aware if you see the word truncate, you always round down. And we could be a little bit more complicated here, and we could talk about the error intervals. So think about what numbers we could truncate and get to 4.85. Well, the smallest number would be 4.85 itself, because we know it's got to start with that. The biggest number would be 4.8599999 ... So we'll do the same sort of thing we said before and swap that out for just saying less than 4.86. So our error interval here is 4.85 to 4.86. That's different to if we were doing an error interval for a rounding to two decimal places. Similarly, we're going to truncate a number to two significant figures and get 83. The 3 is our second significant figure. 83 is obviously the smallest we could have, and then the biggest we could have would be like 83.999 ... So we'll just say less than 84. So in general for truncation, the lower bound is just whatever you truncated it to. The upper bound is just with the last digit increased by 1. So for example here, if we had 7.2 truncated to two significant figures, the lower bound is just 7.2, it's just the same number. The upper bound, we change that 2 to a 3. So you don't have to think about it too much. So the last thing we're going to do is look at the idea of using these error intervals in context, which just means using the words in the question. We've got a sofa here which is 208 centimeters long to the nearest 2 centimeters. So let's do our error interval. It was rounded to the nearest 2, so we halve that to get 1. Then we add that onto our number to get our upper bound, and we take it away to get our lower bound. So our sofa is somewhere between 207 and 209 centimeters long. The space for the sofa is 210 to the nearest 5. So again, we could go 5 divided by 2, which is 2.5. And we can find the space of the sofa is 205 up to 212.5. And the question is, will the sofa definitely fit? And the answer for that is no. Now, in terms of explaining it, the sofa, according to our error interval, could be 209 centimeters, and the space could be 207.5. That wouldn't fit. So as far as where are the marks coming from in this question, there's 1 mark for showing the error interval for the sofa, there's 1 mark for the error interval for the space, and then there's 1 mark for seeing how those two numbers interact with each other. Let's look at another example here. Ribbon is 7 centimeters to the nearest millimeter. Now, millimeters are this bit in centimeters, so we've essentially rounded to the nearest 0.1 centimeters. What's the error interval for the total length of 10 pieces of ribbon? Well, for our 1 piece, we can do the same thing we've normally done. It's rounded to the nearest 0.1, so we should halve that. Gets 0.05. Take it away to get our lower bound. Add it on to get our upper bound. So our ribbon is somewhere between 6.95 and 7.05. What about 10 pieces? Well, the largest they could all be is if we multiplied the upper bound by 10, and the smallest they could be would be if we just multiplied the lower bound by 10. So we end up with the 10 pieces of ribbon are somewhere between 69.5 and 70.5. Here's an example where we've got to think about whole number amounts. We've got the attendance at a hockey game given as 6,000 to the nearest 100. This time it doesn't ask for an error interval, it asks for upper bound and lower bound. That's just either end of your interval. We should still do 100 divided by 2 is 50, and take that away to get that it's 5,950 is our lower bound, but our upper bound is 6049 because we can't have 0.9 of a person. Last year the same game had an attendance of 6,400 to the nearest 10. So the upper lower bound there, again, we'll do 10 divided by 2, which is 5. Add it on to get our upper bound, 6404. Remember, it can't be a decimal. And 6395. So our lower bound was 6395, our upper bound was 6404. Okay, good. What's the biggest possible change in attendance from last year to this year? So the biggest change we could have had would be from the upper bound the previous year to the lower bound the year before that. That's the biggest difference between those two numbers. So we just then have to do a subtraction to find that difference. And we should get that that's 454. Okay, very last question here. We've got a car driving 300 to the nearest 10 in a time of 8.6 to the nearest 0.1. This is a distance, speed, time question, so it's worth reminding you that's what our triangle looks like. Let's go through. Error interval for the distance travelled, it was 300 to the nearest 10. So we should halve that 10, add it on to 300, take it away from 300. There's our error interval. What about the time taken? Well, it was 0.1 divided by 2 is 0.05. Add it on, 8.65. Take it away, 8.55. These can be decimals, so this is fine. So our time is somewhere between 8.55 and 8.65. Upper and lower bound for the speed of the car. Now, if we want to find the speed of the car, we want to do distance divided by time. And have a think about this. If we wanted to find the upper bound for that, we would need to do a large distance divided by a small time. If we want to get the biggest answer to our question. So we're going to take the upper bound for the distance and the lower bound for the time. Now that would give us 35.67 meters per second. What about the lower bound? Well, if we wanted to do the lower bound, if we want to get this to be as small as possible, we would need to do a small distance divided by a large time. So in this case, we're going to need to do 295, our lower bound for the distance, divided by 8.65, which is our upper bound for the time. And that would only give us 34.1 meters per second. Now, this sort of question we're going to look at a lot more next week, but I just wanted to introduce it to you to finish off the lesson. Okay, folks, have a good week.